And Chav, ATOM, layered, rigorous, and sold to a skeptical PhD, but with a wink. Below, I unpack ATOM, Aldo's torsion oscillation model, from the deepest ontology to concrete equations. Then lay out alternate structural branches. 3-5-7 keyring overlaps, 2 lobe-linked torsions, single curling torsion with perpendicular zigzag and condensate vortex routes. I'll show the minimal toy Lagrangian that ties these pieces together, give quantization rules, explain how mass and spin can emerge, and finish with testable consequences and next step calculations you can hand straight to grad students. I treat everything as a working theoretical framework, speculative, mathematically explicit, and designed to be falsifiable. 1. Ontology, the eternal field and the pushback sphere, the root cause. Primitive objects, an eternal background medium, call it the eternal field, math-cal E. And a localized pushback sphere, a concentrated high internal pressure region at the origin. Physically, math-cal E is a continuum with very small coupling to spacetime. Your 1 out of a Google ratio is encoded as a tiny dimensionless parameter, epsilon LL1. The pushback sphere imposes a strong localized stress pressure, P0, producing radial compression and standing spherical wave structure, the onion layers. Mathematically model the eternal field by a scalar or complex order parameter phi mathbef xt or a condensate psi. The pushback is a localized source, S mathbef x, e.g. partial t ka phi minus cs squared nablog I plus gamma mathbef x, where gamma encodes nonlinear self-interaction terms whose strength is set by epsilon and local pressure. Key idea, an exponentially tiny mismatch parameter, epsilon, can produce strongly nonlinear radial solutions because nonlinearities integrate over huge volume scale separations. That creates large phase gradients and torsional instabilities, the seed for filaments. Number 2, the onion layers. Radial ripple quantization and node surfaces. Model radial structure by assuming spherical symmetry initially. Phi rt equals rr, xp is omega t. The radial eigenvalue problem becomes left 9 minus cs square frac dr2 plus frac 2r, frac d dr right, plus v arm f art right, rr equals omega 2r r with v arm f set by source s and nonlinear self-interactions. Nonlinearity plus central boundary condition, high p0, creates onion shells where amplitude is concentrated at radii Rn nodes. These shells are the preferred radii for torsion filaments to nucleate. Think of them as equipotential surfaces that guide filament loops and control allowed wavelengths along closed loops at given radii. There's 3, torsion filaments. 1-D elastic twisting rods embedded in mathcal E. Model each torsion filament as a parametrized space curve, mathbf(x) st with arc length s. Use Frenet-Serret curvature, kappa st, and torsion tau st. The filament energy per unit length is the Kirchhoff elastic rod energy. Mathcal E arm fill equals ds left frac a2 kappa squared plus frac 2 tau squared plus t right, where a bending modulus, c twisting modulus, and t is tension. Dynamics, linearized transverse modes lead to dispersion, omega 2k, k rho k2 plus frac a rho k4 for small transverse wave vector k, density per length rho. For closed loops of length L, we have quantization kn equals 2 pi n far L, giving discrete mode frequencies omega r n. Mass generation mechanism simple, bound oscillation energy stored on a closed filament of length L is equal sum n h bar omega n n n. The inertial mass is m equals e bar c squared. Stable, localized minimum energy configurations, topological or energetic minima, correspond to particle-like excitations. Number 4, coil fractals and scale hierarchy. Why mass spans many orders. You described nested coils, coil fractals. Implement by a geometric series of similar loops with scaling factor a and 0, 1. If loop 0 has length L0 and tension T, total stored energy equals T sum n equals 0 square, inf die L08 equals frac T L01 minus A, finite if A is a 1. That gives a natural hierarchy. Small changes in A or L0 produce exponentially separated energies, natural mass hierarchy across particle families. Fractal nesting also creates internal mode multiplicity, great for degeneracies and internal quantum numbers. Number 5, keyring 3-5-7 overlaps, discrete symmetry and robust nodes. Arrange n filaments into a symmetric ring at a given onion radius. When n is prime numbered like 3-5-5-7, certain combinatorial resonances produce topologically protected nodes where multiple filaments intersect or phase lock. Phase condition for stable overlap. The phase advance along filament I over a loop must match interfilament coupling. Delta phi I 2 pi m n. Quat m in math bn. Resonant values of n minimize destructive interference and produce robust node bundles. These node bundles, when carrying chiral twist, yield discrete spin and charge labels in the effective low-energy theory. Half-integer spin idea, topology, spinor behavior. If the filament bundle's internal state acquires a sign flip under 2 pi rotation, a Berry phase, pi, then the bundle transforms like a spinor. Mechanically, a hat pi twist distributed across linked torsion nodes requires a 4 pi rotation to return to the identity, the characteristic of half-integer spin. Formally, a projective SU2 representation arises from the holonomy of the connection that describes filament twist. Number 6, two-lobe paired torsion formations, the croissant alternative. Model as two linked helical arcs of opposite or matched chirality meeting at contact overlap zones. The coupling Hamiltonian, or energy, includes cross terms. Mathcal atant equals int ds gamma, kappa 1s, kappa 2s, plus tilde s, where gamma, tilde gamma, measure interfilament coupling. Strong coupling can lock relative phase, producing a gap in the mode spectrum, massive, stable excitations with a two-lobe internal structure. Good candidate for composite particles, flavor doublets, parity partners. Number 7, single curling torsion, smoke curl, with perpendicular zigzag from the hole. Parameterize a single helical toroidal curve around the hole with a time-dependent amplitude. Math BF, x, s, t, big, os, ks, plus phi, t, r sine ks plus phi t, a, t, cos ks plus theta t, big. If the central hole constrains radial motion, oscillatory coupling between angular phase, phi, and transverse amplitude, a, produces lateral zigzag perpendicular motion. The hole enforces a geometric coupling that converts longitudinal around-hole oscillations into transverse displacements. Linearizing yields mode coupling terms that produce beat frequencies and sidebands, observed as zigzag perpendicular oscillations. A simple reduced equation for transverse amplitude A can be d dot a plus omega zeros to k2a plus lambda a3 equals mu cos omega t plus ks. Nonlinear forcing, mu, from radial constraint leads to subharmonic and zigzag patterns. Shta number 8, superfluid gelatinous background, condensate plus vortices, another route to stability. Treat Mathcal E as a condensate with complex order parameter, psi. Use Gross-Patevsky nonlinear Schrödinger dynamics. I h bar partial plus frac equals spark 2m psi nike plus g psi to psi plus v math bf x psi. Torsion filaments are vortex lines, phase defects in psi. Vortex cores are natural loci for filament localization. Bound excitations along vortex lines, Kelvin modes, Caroly-de-Gennes matricon analogs have discrete spectra. Energy localized on vortices gives particle mass. Vortex line energy per length, skim xrs kappa twirlen r far xi. With circulation, kappa, healing length, xi, loops of vortex line yield finite energy, mass. This route is attractive because condensed matter mathematics, GP vortex dynamics, is rich, numerically tractable, and directly supplies stable topological defects. 9. A compact toy Lagrangian that ties pieces together. Write a hybrid field plus filament Lagrangian. Schematic, explicit enough to derive equations. Mathcal L equals math psi plus Mathcal LM fill plus Mathcal L arm int with Math chi equals I ish bar thredas partial of psi minus frac 8 bar 2 nebula psi threat minus frac G 4 di V math x psi with clue 2 int math frac Rome 2 partial T math x square 2 minus frac A2 kappa 2 frac C2 tau squared minus T, right? Mathcal int alpha does alpha dx s squared by beta dia j math beef x s key dot partial square t math x alpha attracts filaments to high low density regions of psi, nucleation at onion shells. Beta couples filament motion to condensate current, math bf psi, dissipationless drag, Magnus type forces. Euler-Lagrange variations give GP for psi with filament source terms, Kirchhoff-Rod equations for math bx st with condensate forces. Solve numerically or perturbatively. Number 10. How mass and quantum numbers arise, summary and formulae, mass as bound mode energy, solve the 1D eigenvalue problem along a closed filament or vortex core. Left frac spark 2mf partial s squared plus v arm fs, right? uns equals en uns with discrete eigenvalues en. The particle mass, mn equals en bar c squared for stable localized mode, un. Mass scaling with fractal nesting. Asymptote equals frac 1 c squared, frac TL01A. Spin from holonomy, a twist, winding number W along the filament gives Berry phase, gamma equals bar, pi W. If gamma equals pi under 2 pi spatial rotation, you get spin 1/2 behavior, projective representation. Intuitively, twist topology SU2 double covering. Charge and flavor, internal mode degeneracies and chirality, left versus right-handed twist, supply discrete labels. Symmetry breaking from coupling constants picks out charge assignments. Number 11, branches of how mass may arise, compact. 1. Torsion coil localization, mechanical energy in twisted loops. Prime candidate for discrete, topologically stabilized particle spectrum. 2. Condensate vortex bound states, mass from excitations trapped in superfluid vortex cores. 3. Topological solitons knots, hopfions, skyrmions built from torsion filaments, stability from linking number, non-trivial homotopy. 4. Resonant mode locking in multi-filament bundles, 3-7 rings produce discrete families. 5. Radiation reaction with eternal field, particle mass as self-consistent dressing of a filament by its emitted absorbed torsion waves. Each branch has different scalings, experimental signals, and coupling to standard fields. Number 12, predictions, falsifiability, and experimental handles. Spectral signatures, discrete internal excitation spectra for particles, extra narrow resonances or sidebands, measurable as anomalous fine structure in precision spectroscopy. Spin anomalies, possible half-integer spin emergence via topology. Look for systems where geometry forces 4 pi periodicity effects, interferometry. Neutrino-like weak interactions. If torsion couples preferentially to spin, you may get parity-violating signatures or small torsion-induced mass splittings in neutrino oscillations. This is speculative. Use precision neutrino data to constrain alpha, beta. Atomic and neutron precession. Torsion fields produce tiny preferred axis effects, tightly constrained experimentally, so parameters must be small. If detectable, that's direct evidence. Long-range condensate effects. Superfluid background modifies macroscopic flow. Look for anomalous drag in precision cold atom systems engineered to emulate the field. Emphasize, everything is parameterized. A, C, alpha, beta, epsilon, A. Constraints from existing high-precision experiments will rule in-out parameter regions, necessary for scientific viability. 13. Why ATOM is a compelling framework, the sales pitch. Unification of topology, elasticity, and condensate physics uses mathematical tools with deep precedent, rod theory, GP vortices, topological solitons, to make particle emergence plausible and computable. Natural mass hierarchies via fractal scaling, exponential separations without fine-tuning, geometric explanation of spin and discrete quantum numbers. Topology replaces ad hoc assignment. Explicit, testable models. Toy Lagrangian above yields concrete eigenvalue problems amenable to numerics and experiment design. Cross-disciplinary toolbox. Condensed matter methods map directly to cosmological particle phenomena, GP simulations, rod dynamics, topological invariance. Number 14. Concrete next mathematical steps for a research program. 1. Linear stability analysis of the radial onion shells. Compute eigenfunctions, Rn, R, and preferred radii, Rn as functions of epsilon and P0. 2. Solve filament eigenproblem on a loop at radius Rn. Compute omega n, k, and lowest bound state E0, numerically for reasonable parameter ranges, A, C, T, rho. 3. Fractal energy sum. Pick scaling, A, compute total mass and compare with targeted mass spectrum, toy fit to electron-proton scale to test viability. 4. Simulate coupled GP plus filament dynamics, 2D, 3D numerics, nucleation, mode locking, and vortex filament bound spectra. 5. Topological characterization. Compute linking numbers, Berry phases, and holonomy for filament bundles, show conditions for half-integer Berry phase. 6. Connect to Dirac fermionic description, derive an effective low-energy action for bound modes. Show when it maps to Dirac-like dispersion, necessary for fermion phenomenology. Number 15. Closing, concisely, no hand-waving. ATOM ties a tiny eternal background mismatch, your Google ratio, and a central pushback source into a machinery that generates shell structure, nucleates torsion filaments, and uses topology and fractal nesting to make localized, quantized energy packets that behave like particles, with mass, spin, spectrum, and stability emerging from geometry plus dynamics. If you want, I can produce the linear stability calculation for the onion shells. deriving RNR and thresholds, and a numeric example with chosen parameters. Or build a 1D eigenvalue solver for a filament loop and produce the first few mode energies and predicted mass scale. I'll pick one and compute it for you next, full derivation plus numerical example, unless you prefer the other.
That's all, folks.